So, welcome, ladies and gentlemen, to a session of the time. So it's our pleasure to have Cach as a speaker today. So Jakub was a student of the mathematical modeling here, the master student. I was a PhD student of parallel to law, working on mechanics of numerics of mechanics of fluids and so on. So thanks a lot.
Thank you for the introduction and for the invitation. I'm very happy to be here sharing with you today my research. The presentation is based on a portrait of the paper that we sent already last year for publication in JSM, and now we are currently going through reviews. This is joint work with multiple people, as this is kind of multidisciplinary topic, which contains as well as numerics as well as BDE theory. So there is Karel Duma, which is my supervisor, Jan Blechta and Sebastian Schwarzacher. I hope you are very well familiar with these guys. As the title suggests, we are gonna be dealing with Navier-Stokes equations. We are gonna be investigating various bifurcations and flow transitions in one two-dimensional setup. The flow is governed by the Navier-Stokes equations, and the main player today is gonna be the direction, which is defined here. This is Cauchy stress tensor, and if you multiply it with the normal to the boundary of interest, you get the direction vector, which is a function or a distribution depending on the regularity of the solution. But let's say for our purposes it's function, and we are gonna parameterize it with some parameter theta, because we are gonna be investigating the direction along the boundary of the circle. So theta is gonna be an angle, and we are gonna be interested in Reynolds number. We are gonna be thinking about this as a parameter to solution map. That for Reynolds number we can obtain a solution. The discretization and the solution to the equations is quite standard. We are using Fargray library, which is finite element library with high level of user. User can adapt the code in almost any way. For the discretization, we are gonna use Taylor-Hood these continuous elements because they are standard, and for the purposes that we need are sufficient. The time discretization of the unsteady equations is gonna be done by the Crank-Nicholson scheme with even though it's stable, astable, and so on, but also with sufficiently small time step, so everything is fine in time, and we are gonna solve the resulting system in monolithic way, meaning that we solve the couple of equations together. This is particularly useful when we can do Newton plus LU decomposition, and we can remember that we can reuse the LU decomposition over multiple Newton steps, even like multiple time steps, which is very efficient. Well, and this is the Shepherd-Wright benchmark that we are going to be investigating today. We have inflow, parabolic inflow on the left, outflow, direction-free outflow on the right, no slip everywhere else, and the main interest is gonna be the obstacle here, which is placed a little bit off center, just to order to get bifurcations for a little bit lower Reynolds numbers to save some computational effort, but that's it. And we are gonna be we identify the components of the direction along the main axis, which is very convenient for this choice because these are kind of like symmetry axis, like symmetry over the width, and like the downstream part. And my aim today is to persuade you by we are studying the traction, what can we see in the traction and so on. We are gonna be studying the transitions in these configurations I showed up to the Reynolds number 1000, and we are gonna observe various bifurcation phenomena, and we are gonna track them, and later we are gonna try to a posteriori connect the critical points that I will show what does it mean in the traction profiles, traction around the cylinder, to these bifurcations phenomena, and I'm going to show you that all the bifurcations phenomena leave some footprint on the obstacle. And we also try to interpret the results in our kind of like new framework. And yeah, we are gonna also discuss some open questions in PD theory, how it connects to like uniqueness in one path in time, and the long time orbits of the dynamical system. So this is kind of teaser what all the bifurcations are we are gonna be expecting. So from zero Reynolds number, which can mean the Stokes flow or the zero velocity, because we chose the Reynolds number in such a way that we increase the velocity profile, the peak of the velocity profile, and by this mechanism we increase the Reynolds number. So we can explain the zero either as the Stokes limit or the hydrostatics. Nevertheless, we increase the Reynolds number. We are having some laminar flow, which then turns to flow with the circulation zones behind the cylinder. Then finally, the flow will become time periodic, which is kind of from the viewpoint of PD theory, this is open questions whether such flow is unique and so on. And we are gonna get much more. Okay, so what is turning point? So we have our obstacle, we have some flow, we can compute the traction, I think, on the boundary, and we get traction either the drag or lift as a scalar function along the boundary of the cylinder. And I'm having here two plots, one for the Reynolds number 7 and one for the Reynolds number 9, which is like the midpoint where the transition from laminar flow to flow with recirculations happened. And what we notice is this point, which we are gonna call turning point, where the traction kind of stays same with the increasing Reynolds number. Later, these critical points we will track these critical points systematically, and we will try to move them back to all other bifurcations. We will always deal with the steady traction, because kind of like when the flow turns time periodic, and we should investigate the traction function over the period of the flow. It's kind of more demanding process, so we stick to the steady tractions. And what is very surprising, even in the steady tractions you will get some hints about the bifurcations in the unsteady regime. Well, this is how it looks like when we are sitting here on the cylinder at where the turning point happens. And if we observe the lift is having kind of like local critical behavior. Oops. Yeah. One more thing, why we are even investigating the forces on the obstacle. You can take, for example, the dark crisis, which is very famous phenomenon, where you increase the Reynolds number. for the flow around the obstacle, and suddenly the Reynolds number drops, the flow regime shifts, and the flow patterns kind of chooses the more optimal energy consuming way, so the drag drops. So we are hoping that investigating not the net quantities like net drag, like integrated drag over the whole body, we are gonna be investigating the pointwise function. This is kind of a review of the Navier-Stokes PD theory. So interesting points are that the steady boundary value problem is non-unique in 2D and in 3D, and we are gonna find numerical multiple solutions. Initial boundary value problem is unique in 2D, but we know only a little about uniqueness of time periodic solutions, and if these time periodic orbits from the viewpoint of the dynamical systems are unique. And there is certain question about the eigenvalues and eigenvectors of the linear Navier-Stokes operator and also of the nonlinear Navier-Stokes operator, whether when you compute the eigenmodes, how they compete, if other one eigenmode can trigger another and so on. So these are still open questions. This is how we numerically analyze the results. We are of course gonna solve for the unsteady solution. We are gonna get time periodic velocity field and the pressure, and by global observations of the velocity field, we are gonna classify or even identify that the traction occurred, because that's the only way, because bifurcations in their fundamentals, they are global phenomena, because the irrelevant of the flow geometry, if I have cylinder or not, for example, the first of bifurcation will occur. So there's no other way than to look on the global velocity field. We are gonna be also forcing the solutions to stay steady by canceling the time derivative of the velocity and look on this solution. We are gonna investigate the traction profile of the steady solutions, and we also gonna look on the eigenvalues and on the multiple steady solutions. So this is how the search for the linearized eigenvalues look like. You take some base flow, you add perturbation, you get equations, you get generalized eigenvalue problem, you solve it, respectively, you get eigenvalues and eigenvectors. And you can do this in 2D, or you can even assume that this perturbation is 3D, and you can try to get some 3D modes appearing. Well, these are the results for the first portion of the Reynolds numbers. Unfortunately, the pictures are quite blunt, so I'm gonna describe what's happening. So we have somehow perfectly laminar flow around the cylinder, and then the recirculation zone starts appearing, and their appearance, it's not sudden. It's kind of like they are holding there, and finally they somehow settle. This is, of course, as I already discussed, mirrored in the traction by its turning point. This is the local. Sorry. This is the local viewpoint, and we also can have global viewpoint, which is gonna be the final result of this talk. So I will guide you through this picture. So we have location coordinate here from minus pi to pi. It's angle on the circle. 0 is at where the it's the first point that the flow hits. It's the point on the left hand side of the circle, and we are increasing the Reynolds number. And what does this black line shows is the critical all the critical points, all the points where the first derivative, the first vector Reynolds number is 0. And we can see that here at 7, where the recirculation zone appeared, we kind of hit it. The curve is here locally flat. And these are gonna be then other conditions that we need to pose on like empirical conditions that we experimentally find, that we need to pose on the traction in order to identify the transitions in the flow. And from the bifurcation theory point of view, these conditions are kind of natural, because in bifurcation theory you study like these faults, like these U faults, when the curve faults either this way or this way. So you study this all the time. Yes, and we of course are gonna be studying for the lift and for the drag of the traction separately. So then we increase the Reynolds number. Nothing is happening until you get this behavior. So for a long time, the solution stays steady, but the flow is oscillating on the machine precision. Like if you are solving, you are getting the linear system, you are plugging back to the equation, you are getting the residuum, and the residuum is fluctuating around the numerical precision. But somehow, if you wait for the long time, the global oscillations appears, and this is commonly, and to this phenomenon, it's commonly referred as first of bifurcation, which means the steady solution is no longer stable, and the flow prefers another pattern. As I discussed, we can this is already very well established that first of bifurcation can be found in the spectrum of the linear Navier-Stokes operator, and it in some sense converges, or it's the correct result even for the full Navier-Stokes operator. And the point is here that if you are getting your eigenvalues, pair of eigenvalues crosses the real axis, sorry, the imaginary axis, and the imaginary part of the number is kind of the frequency of the oscillations up to the factor of 2 pi. And we can get to this eigenmode, we can associate its eigenvector, and if we take the steady base flow and plus the eigenvector, we can reconstruct the solution, and it matches very well the real solution I showed here. So this is good. And the main point is that we get another critical point or turning point, how we call them in the traction. Now in the drag, here we have some local critical behavior of the drag, and from the global view, again we have theta coordinate, we have Reynolds number, and we get U fault in the critical line. And from this point now on, all the steady solutions are unstable, but it doesn't mean that to solve for the steady one is pointless. There that you will just, if you start the unsteady simulation, you will converge, you will diverge away from this steady solution. And now we will have some another flow transitions, rather, kind of minor. For example, the onset of the wall effect, which means that if we increase the Reynolds number, the weight behind the cylinder gets wider and wider, and at some point it hits the wall, and some kind of vortices that are convected along the walls appears. This happens at Reynolds number 78. And also interesting thing is that at Reynolds around 78, at Reynolds 75, we found a 3D bifurcation in the, like, we did the linear perturbation thing with the 3D perturbation, and we found another we found like bifurcation in the steady state, which looks like that you have some spatial periodic behavior in the length of the vortex along the spanwise direction that you don't see. This plot just shows that for the Reynolds number, we kind of switches from the eigenvalue, its negative parts turns from the negative values to the positive one. And for the spanwise like periodicity where this happens, this periodicity needs to be minimal, and so on. Anyway, just another type of bifurcation. The interesting thing is again in the tractions. Now again in the lift, we get another U-fold, which is there. It is kind of flat, so it can be 78, it can be 75, who knows? There we can, establish this error or kind of uncertainty from the sparseness of our data, the grid in Reynolds number and grid in the theta coordinate. But anyway, there might be it can be connected to one of these bifurcations happening. Okay, now I hope that somehow this is gonna work. Yes, so this is just one time period of the flow. Yeah, this is the pointwise lift, and this is the pointwise drag, and they just wobble. Anyway, there is another 3D bifurcations now in the unsteady solution, which means that the vortex that we are getting gets the spatial, it starts to be spatially periodic. This computation was out of scope of our work, but in the literature we found based a lot of work reported this phenomena around the Reynolds number 190, which kind of fits our fault in the curve at 177. This is interesting bifurcation. This is multiplicity in the steady state, as we discussed. The steady solutions are not unique, and we use deflated continuations, which means that we found one steady solution, then we can kind of bend it, and we force the Newton iterations to converge away. And this we did for the whole range of the Reynolds number, and this number 350 we found this bifurcations, which is kind of pitchfork bifurcations, but a little bit imperfect because our cylinder is not perfectly placed in the center of the channel. So this is on the y-axis we have symmetry deviation metric, which is kind of like integral over the mirrored domain, and we can see all three branches in imperfect pitchfork diagram. This is also very well established in the pseudospectra of the hydrodynamics, which then says that there should be a real eigenvalue that should hit zero value. At this point, the new steady solutions should appear, and we kind of get it, but not really. But we don't need to see from them directly. And this is just visualization of the three solutions. Yes, at least backup is gonna. Yes, this should just demonstrate that even though the flow pattern around the cylinder looks same for all the simulations, the lift, the net lift integrated around the cylinder is kind of still mystery. It behaves very strangely, and it just showcased that the lift is really sensitive to asymmetry in the flow. And of course, we see this bifurcation in our little diagram now in both lift and drag. So if we look at 315 Reynolds number, we are gonna see that we have faults in the lift and also in the drag on multiple places. From now on, it's not really sure which branch we should follow with our procedure of studying the steady traction. Anyway, we chose the solution that was that we denoted as a baseline branch that was kind of like natural that our code somehow solved for from the first place. But anyway, for a higher Reynolds number, we couldn't get any good signal or any faults. The lines are almost the straight lines, so that there's either uncertainty or it stops to be a good observable. There is one small thing that is this asymmetric shading, vortex shading. I hope it's gonna be visible from this point on, where the steady solutions broke the symmetry. Also the unsteady solutions broke the symmetry, and I hope it's visible that the vertices adducted on the top wall are much greater than the vertices adducted along the bottom wall. And then we were able to locate only one last bifurcation, and it's the onset of one Karman vortex street, which means that now the kind of recirculation zones or the vortices, if you like, are advected downstream, because before they decayed, they stop being there after only one spatial period. And as I said, our lines became very straight in our diagram, and we could not really reliable locate any faults in our curves. to associate them with this last bifurcations, the bifurcation that we found. Well, either it's because it stops being a sensitive indicator, or how my colleague Sebastian Schwarzacher like to interpret this result is that that you don't longer need the cylinder, that the flow is gonna be more chaotic, problematic, because of the convective term is already quite dominant for large Reynolds numbers. Anyway, so this is kind of already. This is. Sorry. I was just confused with the time, sorry. This is kind of already summary. I just had panic attack because I thought I just used 10 minutes, but I used 30, so that's good. Yes, so these are all the unsteady bifurcations into D that we observed, and now we try to measure them to all other phenomena, or to like globally visible bifurcations in the velocity field, and also to the events that can be seen by linear perturbation theory. So we've already seen this diagram, and we have signals in drag at 0, which could be interpreted as that we came from hydrostatics to actually to some flow actually, and then we have this series of turning points in either lift or drag. The linear theory is not bad at all. It predicts the stability of the steady state very well. It predicts the unstable complex eigenmode very well, and it also suggests the appearance of the multiple steady solutions. Yeah, this is just to remind that at the end, what we found that not all the critical points, not every point on the curve is the turning point that we call. Only these few folds that are here or here. And for this, we can geometrically find following conditions. So we are on our curve. Here C stands for the component, so it's either lift or drag. And the first one says that the derivative with respect to theta must be 0, so which is the geometrical condition for this event. And then we have that the second order derivative with respect to Reynolds number must be 0, which is geometrical condition for all these particle events. And we try to interpret these conditions in the framework of already established classical bifurcation theory. So we are on our critical curves, and these conditions would suggest that something is happening for the first time, which would be in correspondence would be observed that the recirculation zones appear, and then the vortex shouldn't appear, and these and what this means is that the solution is insensitive to the up to the second order to the change in parameter, which in the classical theory suggests some higher order degeneracy, which means that the phenomenon is already there, but it's gonna change slightly. So if we look into our little table, so we have onset of steady vortices, and we have first of bifurcation for the condition of type A, something is happening for the first time. And we have all these other like Weger organization effects, 3D instability on set and multiple steady solutions that we kind of see as a secondary effect. And we can also try to interpret the appearance in lift or drag. In drag, it's usually interpreted as as a symmetric event that propagates downstream, whether in the lift it's usually interpreted as some kind of asymmetric effect happening in the perpendicular direction, which we kind of observed because first hop bifurcations in this sense should belong to drag, and and the Baker organization, the appearance of the of the wall vertices and the symmetry breaking of the solution should go to lift. This just summarize what I just said, so we can proceed. And this brings me to the summary. So we observe that pointwise traction on the obstacle can contain information about the bifurcations appearing in the flow. It either lift or drag, both are kind of good indicators, and it would be very beneficial to kind of proceed with this and try to apply it to more general flow geometries and so on. We find the correspondence between critical Reynolds numbers and turning points, and we try to interpret the drag and the lift response in different way. I have this small comment about the existence of unique time predictable in time attractor. In our simulations, we tried to kind of force the flow to produce two different patterns for one set of data. So we can, for example, when the symmetry breaking occurred and we had three multiple steady solutions, we tried to start the simulations from each one of them, and we always converge to the same flow pattern. So we tried to find multiple of them. We find. Let's see. Yeah, and I would be very happy for your questions, remarks, and suggestions. Thank you.